All right, guys. So let's start talking about what our strategy is going to be for exploiting SCH overflow and getting past depth and GS protection and all that other kind of nastiness. So to do this, we always have to rely on like one weak module. It's generally a necessity unless you have like an information leak bug. So those are sort of the two avenues you can take here. Is that one is you're abusing a weak DLL like we're going to with Flash, or you can use a information disclosure bug to figure out what the state of the stack is or figure out where some processes, where some functions are located. But we're not going to take that route. Apparently, the rumor is any sort of bug that allows you to gain control of EIP can be massaged into an information disclosure bug. But a lot of times I think it's just easier to abuse these weak modules where we know exactly what their address range is going to be. Like in Windows 7, even with ASLR, Flash will be loaded at this address. And does not have state SCH turned on, so we can return to any of its code if we overwrite the exception handler. So Flash is the little person we're going to beat up on today. Okay. So in terms of GS protection, don't care about that. We already know how to get past it. We're just going to, instead of overwriting the return address, overwrite the exception handler. We'll gain control of EIP before that stack canary is ever checked. When we gain control of EIP, we're going to call virtual protect. We're going to change the permissions on the page where our shellcode exists to be executable, and then we're going to return to our shellcode. So it sounds pretty simple in theory, right? There's actually like a lot of little annoying things that will come up along the way that I'm sure you'll all discover and enjoy. Okay, so since we're going to bypass GS protection, we're going to overwrite the exception handler. The problem is when we gain control of EIP via an exception handler overwrite, we do not have control of the stack pointer. ESP is pointing at not attacker-controlled data. So I can actually show this. Let's see here. I'm going to run SCH overflow again, and I'm just going to set the address of the exception handler equal to a breakpoint function. Just because I want to show you guys where the stack is pointing when we gain control of EIP via an exception handler override. So I'm going to use just this one right here, I guess. Here's 04014.9C, okay. All right, so at this point, this is the exact point we've gained control of EIP. And for return-oriented programming to work, we have to control the stack pointer. It's like the most important part of return-oriented programming. The stack and the return instructions are the glue that holds all of the code together that we want to chain together. So right now, ESP points to 12F6B8. And look at that, it's not any of our data, right? Because we've overridden the stack with deadbeef and other stuff. And none of this is deadbeef, so ESP is not pointing anywhere close to where our data is at. And we have to make ESP point to our data because when a return instruction executes, we need to continue to control EIP. If a return instruction executed right now, we would not control EIP because it would just pop this value off the stack and put it into EIP. Okay, so the program we're going to be using, I've actually put into, I've turned on some extra mitigations and put it in a different directory. It's in SCH overflow hardened. And so this is the one that we'll actually be attacking for today, not the original one, but this one, because I've recompiled it with some additional mitigations turned on, like safe SCH and GS and all that business. And what I want you to do is kind of do what I just did. Develop a payload that overrides the exception handler with the address of an OXCC byte and a flash binary so that it will break when you gain control of EIP, and that exception handler is processed will break. I want you to look at where ESP is, and I want you to figure out what the delta is, what the difference is between where ESP is pointing now when you gain control of EIP and where your actual data is. Tell me how big that gap is. Does that make sense, what I'm asking you guys to do?
Do we need to reboot into dev?
Yes, everyone, if you haven't already, reboot into dev. Notice dev won't stop us from doing that because we're just returning the code that already exists that's marked as executable. Okay, so I'm going to walk through the process of trying to get to where you guys are on my screen if anyone wants to follow along and feels confused at this point. So at this point, I'm just running it with a file full of 2048 bytes of deadbeef because I just want to calculate again the offset to the file where we're overriding that exception handler function pointer.
Where did you get P0? Or the FFP0?
Being exchange. Yeah, that's just the first exception handler that we're going to override. What I'm going to do now is just override those with some placeholder values to make sure I am demonstrating control over EIP. Okay. What we expected, so now I just need to find a CC byte to point it at, and I need it to be in the flash binary since I believe safe SCH should be turned on and everything else. We can check with gnarly. Okay, so the address I found for the flash CC byte that I'm using, if anyone is following along with what I'm doing, is 1009D8D8. Then once you got to this point, you should go look at where ESP is pointing. Try to figure out where your data is. Figure out the difference between the two. In fact, what I want you to find is the deltas for the absolute difference. So like the delta from the start of your data and the delta to the end of your data. So you should find x such that ESP plus x equals start of attacker data. Find x. Just want to be sure that everyone understands why it's important that the stack points at attacker data, so everyone understand why that's important. We have to make sure when those return instructions execute that we maintain control of EIP. We do not control ESP. We will not maintain control of EIP across return instructions. The stack is the glue we're going to chain all these pieces of code together with. So we have to have that glue. Now, when you have a typical stack overflow, you have control of ESP by default, because ESP will end up pointing right above that saved return address that you corrupted, and that will all be stuff that you've overwritten, so you'll automatically have control over ESP. With these exception handler overrides, you do not automatically have control over ESP. So we're going to need to get control of it somehow. So you guys can, curious who has the answer to these questions. This is the easiest question. Just any Z such that ESP plus Z equals attacker control data. And then the harder questions are what are X and Y, so these are taking the absolute limits of the attacker control data. Does anyone have an answer yet? So these are the questions you should be asking yourself. So I'll write down what Zeno got here. We'll see if other people got the same thing. Has anyone else got some answers? Can they confirm what Zeno found? So here's what I would do to figure out these answers for anyone who wants to follow along with me. I already know what the address of buff is because I broke on that called to fread, and I know that's going to be the start of my attacker data. So I know my attacker data starts at 13FB6C. So I can just do some math here in WinDbug to tell me what the answer to X is. With 13FB6C minus ESP. So I get 4AC, it's the same as Zeno. Now I figure out what the limits of that is. So if I remember correctly from yesterday, the buffer we were overflowing was like 1,024 bytes. So I know at least up to 1,024 is going to have the attacker data. So I'll just start looking manually. So then 13FB6C plus 1024. Oh, it's hexadecimal. So that's it's 400. Is that right? Okay, so still attacker data there. 13 EC. Okay, and so at FC plus 4, I no longer have attacker data, so I'll just say FC in my calculation. And 93C, so yeah, Zeno just took the next one, but doesn't matter. The next 4 bytes.
Yeah, I started from 1400, or 140,000, which is what the bang tub displays as the last address, or the end of the stack.
Yeah, I mean it doesn't too much matter the very outer limits because we'll actually want to pivot the stack into like the middle or beginning of the attacker control data. That way we have more room for a return-oriented programming payload. If we were to put ESP, make ESP point to like right here, that could be problematic because then we'd only have this much bytes for our return-oriented programming payload in our big stack frames that we're going to create, the virtual protect call. but I just want you to guys have a general idea what the limits are. Okay, so here's the next step of the lab. We have to make ESP point to attacker-controlled data and then immediately return. The return will allow us to maintain control of EIP, so like point EIP at the next address that we want, and the add ESP, or making ESP point to our data, is important for reasons I've already described. It allows us to continue to maintain control of EIP when multiple returns are executed. So what we need to do is find a series of instructions that make ESP equal to our data. Then execute a return. So essentially what we have to find is a function of the form if we were to point the exception handler function pointer at something described by these constraints, we would point ESP into attacker-controlled data and then gain control of EIP again. So we control the stack and EIP, which is exactly what we need for return-oriented programming. So this is what I want you guys to try to find. And this has to be, I should be more clear, so what we're looking for here is a stack pivot. Generally, the first thing you want to do when you gain control of EIP, and when you're trying to bypass mitigations, is pivot the stack. Find some sort of stack pivot instruction that allows us to gain control of ESP so we can start executing return-oriented programming. So you can search Flash. Oops. Oh, no. And the bytes you're looking for. So you have to figure out what bytes it is you're actually searching for. And I want you guys to try to figure that out as well. So the command to search Flash is, I'll put this in that notepad file too for you guys to have. So what I would do, guys, is I would figure out what are the bytes for add ESP, some like 32-bit value or something like that, and search for those. And I would make sure what I find also ends in C3. It's going to have to end in C3. But I would do that by just starting to search for add ESPX and look at the output to make sure that the output I find ends in C3, because it's going to have to end in that return instruction so we maintain control of EIP. You got one? All right, so what address is it for what you found?
10086 D6A.
Sounds promising. What I remember from the last class. So this is what Dave found. Something that does add ESP878 in return. And right now I'm still broken at that point where we gain control of EIP. So let's do DD ESP plus 878 because that's what a stack would point to after that instruction executes. And look at that, attacker data. Now why don't you describe how you found that, Dave?
Just a search command on 81C4.
And how did you figure out 81C4?
I did an assembly and
Yep.
add ESP or something.
So this is exactly what I would do. I would do, all right, well I know I need to do an add ESP, so I'll do a symbol mode add ESP 100, just give it, I will do them an offset. Hopefully when debug will stop reading out here in a second. Restart with debug. Okay, so I can see using the A command that the bytes for add ESP are 81C4, then like a 32-bit value to add. So I can see like my 100 here, 1000 or 0100 rather. So 81C4 are the bytes for add ESP. So what I'll do is I'll search flash. Okay, and the trick here is, what were you looking for, Dave, in this output when you were trying to find the answer?
Big number. What's that? 81C4.
Yep, and what else?
C3.
C3, that's right. So you want these numbers to match this criteria, this range, bigger than 4IC and less than 940, and it has to be followed by a C3. So it's not that much output. Let's see, too small, 0480. That is just too small, I think. Yep. B2C. Let's see, is that might be too big? Yeah, too big. 878. There's our winner. And then we also have some ones, and see it's followed by a return instruction, and 0600. This might work as well. So we have definitely some different choices here, but Dave's one works just fine. I think it's the one that the last class shows actually, but I believe these 600s work as well. Just so you can verify that it all looks right, you can do disassemble on that address, U1108 E410 at ESP600. Is that ESP plus? Yeah, attacker data too, so that's good too. But since Dave found that one, we can use that one. Hopefully it won't come back and hurt us. Only time will tell. Does anyone have any questions about what it was we were just looking for or how we found it? Everyone feel okay with that? Does everyone understand why we are looking for this stack pivot? You understand the general process I just went through to find it? Now, obviously, using WinDebug to search for this is not great because WinDebug doesn't support regular expressions and so forth. But it's pretty easy to, write a small disassembly script to look for stuff like this in the DLL. And I can actually provide you guys one that I've written myself at the end of class. For now, I want you guys to learn how to do it in WinDebug because we should all get better at WinDebug. How good you are at WinDebug will greatly determine or greatly help how easy it is to develop exploits like this. How good you are at developing exploits is basically directly correlated to how good you are at debugging. So getting good at debugging is helpful, of course. Okay, so here's what I want you guys to do next. Change the exception handler function pointer you're using. Currently, it should be pointing to that CC byte to point to this. All right? And then locate in the file what particular part of the file it will use for that return instruction. What part of the file will end up in EIP. So after you do that, add ESP 800 or whatever it was, ESP is going to be pointing somewhere in here. And then when it sets the return instruction, does the return instruction kind of set EIP equal to one of these values? I want you guys to figure out exactly what offset it is into the file where that is occurring. Once you think you have an answer, try to demonstrate control by changing that part of your file to like AAAA, and make sure after your stack pivot happens, you end up with EIP equals AAA, whatever value you put there. So here's how I would calculate this, guys. Okay, so I'm going to use 878 since that's what you guys found. What I'm going to do is set a breakpoint on that address, on the address of my stack pivot, so that when I begin executing my stack pivot, I'll have the debugger will be in control, and I can start looking at stuff. Also, I want to verify the address of my buffer, because I know the address of my buffer will represent like offset 0 into my file and my payload. Okay, so that's still the same 13FB6C. Just wanted to show you again how I got it. 13FB6C. Got it the same method before when I wrote it down. Oops. Didn't change the address. On payload, let me do that now. 10 6A 60 08 0. Make sure I set the breakpoint right. Yeah, that's right. Okay. So, oops. Just going to write down some stuff I know in this window. I know the address of my buffer is this. And where is ESP going to point to after this line executes? Let's do a single step to find out. Oops. Okay. So that's an attacker data. Yeah, it's all good. So, I think the difference between ESP is pointing now and the address of my buffer. That's the offset I get into my file, 3cc. And so I can try to verify if that's actually correct by changing that offset in my file to a placeholder value and making sure EIP equals that placeholder value. And what I'm going to do just to give myself some wiggle room is put some placeholder values around it as well. So I'll do AAA. B's here. So if my math was exactly right, EIP should equal BB, since that is offset 3cc in my file. But in case I was a little bit off, the wiggle room here, placeholder values all around. Restart. So at this point, I've demonstrated that after my stack pivot, my EIP will point at offset 3cc into the file. Those of you that are getting slightly different offsets but using the same pivot is probably because you're naming your file that you're putting your payload in differently. And your command line parameters end up on the stack, and it can shift stuff around a little bit on the stack. Now, if you wanted to give yourself some real wiggle room and effectively put like a no-op in here, does anyone have any idea of what we would put around here instead of no-ops if we wanted something to act like a no-op in this return-oriented programming world? If we weren't exactly sure what our offsets were. So in return-oriented programming, a no-op is effectively a return instruction. So if we were to fill everything in this area with the return instruction, with the address of a return instruction rather, it would end up somewhere in our return-oriented programming knob sled, do a return, just keep increasing the stack pointer, basically return, until finally we get to what we really want to have the value of EIP for. So in this case, you can just be absolutely precise and not use any return-oriented programming, any ROP knobs. But that is what you could do to effectively like give yourself some padding in this area if you're not exactly sure where you're going to end up in your payload file. So before we move on, I want to make sure that everyone can demonstrate control of EIP after that stack pivot occurs, and everyone knows what offset in their file is actually being popped into EIP after the stack pivot. Does everyone here have that? Okay, so I'm going to walk through how I did this, guys. So anyone that's lost, try to follow along. First thing I'm going to do is set a breakpoint on my call to fread. That way I can see what the address of my buffer is. Because I know the address of my buffer is going to represent offset 0 in my file. Because it starts reading in the beginning of the file and putting it in the beginning of the buffer. So I want to know what that address is. So I'm just going to do like a run to cursor to get there. And looking at the stack right before the call to fread, I can see that my buffer is located at 13FP6C. Can I copy that value? And next I want to see where the stack pointer ends up after I perform that stack pivot that Dave found for us. So, where was that stack pivot again? 100866A. Is that right, guys?
One 008 66A.
1008. And I go up to the point where we start executing my stack pivot. And so after this, add ESP878, it's going to point at attacker data. Just not really sure where in my file that represents. So I'll do T. And now ESP is pointing at attacker data, but I want to know exactly where my attacker data it is. So I'm going to do the difference between ESP and where my buffer starts, 13FB6C. I can see that this means that ESP is now pointing at effectively offset 3CC into my file. So if I were to change that in my file to a placeholder value like B's or A's or C's or whatever, I should eventually see that EIP equals this. So who knows what address we're going to put here? What's the next thing we want to do effectively? Yep.
Well, we'll want to point it to some sort of instruction that disables step.
That's right. So we're actually going to, the very next thing we execute is going to be virtual protect. Virtual protect is a kernel 32 function that allows us to change the memory permissions on pages of memory. We can make them executable or writable or whatever.